The National Electrical Code, or NEC, does have an exception that allows the use of non-self-grounding ground fault circuit interrupters, or GFCIs, under certain circumstances. Specifically, exception 406.3 D2 states that a GFCI is not required to be self-grounding when it is installed in a non-metallic box provided with a grounding means, or in a metal box that is effectively grounded. This exception applies to recessed metal boxes because metal boxes are inherently grounded through their connection to the metal conduit or wire mesh. Therefore, using a GFCI in a recessed metal box without a self-grounding feature is permitted according to the NEC. If a GFCI is not self-grounding, a bonding jumper, typically a green or bare copper wire, is required to connect the GFCI's grounding terminal to the grounding means of the electrical box. This ensures that the grounding path is complete and the GFCI can function properly. It is important to note that all GFCIs installed in non-metallic boxes or metal boxes with no grounding means require a bonding jumper to the box. The purpose of a ground fault circuit interrupter, or GFCI, is to protect people from electrical shock. It does this by monitoring the current flowing in the circuit. If the current flowing out differs from the current returning by more than a very small amount, typically 5 mA, the GFCI trips and cuts off the power. This happens very quickly, in a fraction of a second, preventing a dangerous electrical shock. Grounding is a critical safety feature in electrical systems. It provides a path for fault current to flow back to the source, which causes the circuit breaker to trip and energize the circuit. This prevents dangerous voltages from building up on metal parts of appliances and equipment, reducing the risk of electric shock. A self-grounding device is designed to make a direct connection to ground through its mounting screws. When installed in a properly grounded metal box, the device automatically becomes grounded without the need for a separate bonding jumper. However, not all devices are self-grounding, and even when they are, there may be situations where a bonding jumper is still required to ensure a reliable ground connection. A bonding jumper is a wire used to connect the grounding terminal of a device to the grounding system. It provides a redundant grounding path, ensuring that the device is properly grounded even if the self-grounding connection is compromised. Bonding jumpers are typically required in situations where the metal box is not reliably grounded, such as when it is mounted on a non-conductive surface, or when there are multiple layers of paint or corrosion that could interfere with the ground connection. The NEC specifies the requirements for grounding and bonding in electrical systems. It outlines the conditions under which self-grounding devices are permitted and when bonding jumpers are required. The NEC also provides guidelines for the size and type of grounding conductors that must be used. Exception 406.3 D2 specifically addresses the grounding requirements for GFCIs. It states that a GFCI is not required to be self-grounding when it is installed in a non-metallic box provided with a grounding means, or in a metal box that is effectively grounded. This exception recognizes that metal boxes are inherently grounded through their connection to the metal conduit or wire mesh, which provides a reliable grounding path. However, it is important to ensure that the metal box is indeed effectively grounded. This means that the box must be properly connected to the building's grounding electrode system. If the metal box is not effectively grounded, a bonding jumper will be required to connect the GFCI's grounding terminal to the grounding system. In non-metallic boxes, a grounding means must be provided. This typically involves running a grounding conductor to the box and connecting it to the grounding terminal of the GFCI. The grounding conductor must be properly sized and connected to the building's grounding electrode system. The grounding electrode system is a network of interconnected grounding electrodes such as ground rods, ground plates, and metal water pipes that are used to connect the building's electrical system to the earth. This provides a low impedance path for fault current to flow back to the source, which helps to protect people from electrical shock. When installing a GFCI, it is important to follow the manufacturer's instructions and the requirements of the NEC. This will ensure that the GFCI is properly grounded and will function correctly in the event of a ground fault. If you are unsure about the grounding requirements for a particular installation, it is always best to consult with a qualified electrician. They can assess the situation and determine the appropriate grounding method. In summary, while the NEC does allow for exceptions to self-grounding GFCIs in certain situations, it is crucial to understand the specific requirement and ensure that the GFCI is properly grounded. This will help to protect people from electrical shock and ensure the safe operation of the electrical system. Let's delve deeper into the specifics of GFCI grounding and the relevant NEC exceptions. Ground fault circuit interrupters are essential safety devices designed to protect individuals from electrical shock hazards. They work by monitoring the balance of current between the hot and neutral conductors in a circuit. If a difference of 5 mA or more is detected, indicating a ground fault, the GFCI trips and quickly cuts off power to the circuit, preventing a potentially dangerous shock. Now, let's address the NEC exception that permits the use of non-self-grounding GFCIs under specific conditions. NEC Section 406.3 D2 provides this exception. It states that a GFCI is not required to be self-grounding when installed in a non-metallic box with a grounding means or in a metal box that is effectively grounded. The key here is understanding what constitutes an effectively grounded metal box. An effectively grounded metal box is one that is reliably connected to the building's grounding electrode system. This connection can be achieved through various means such as metal conduit, armored cable, or a dedicated grounding conductor. The purpose of this grounding connection is to provide a low impedance path for fault current to flow back to the source, facilitating the rapid tripping of the circuit breaker or fuse in the event of a ground fault. If a metal box is not effectively grounded, a bonding jumper is required to establish a proper grounding connection for the GFCI. A bonding jumper is a conductor, typically green or bare copper, that connects the grounding terminal of the GFCI to the metal box. This ensures that the GFCI is properly grounded, even if the metal box itself is not adequately grounded. In non-metallic boxes, a grounding means must always be provided. This typically involves running a grounding conductor from the circuit's grounding system to the grounding terminal of the GFCI. The grounding conductor must be properly sized according to the requirements of the NEC, and it must be securely connected to the grounding terminal of the GFCI. It's important to remember that the absence of a self-grounding feature on a GFCI does not eliminate the need for proper grounding. Regardless of whether a GFCI is self-grounding or not, it must always be connected to a properly grounded circuit. The grounding connection provides a vital safety function, protecting individuals from electrical shock hazards. Now let's consider some practical examples to illustrate these concepts. Imagine a scenario where you're installing a GFCI in a recessed metal box in a bathroom. The metal box is connected to metal conduit that runs back to the electrical panel. In this case, the metal box is likely to be considered effectively grounded, and a non-self-grounding GFCI could be used without a bonding jumper. However, it's always a good practice to verify the grounding connection with a multimeter to ensure that the metal box is indeed properly grounded. Alternatively, consider a situation where you're installing a GFCI in a plastic box. In this case, a grounding conductor must be run to the box and connected to the grounding terminal of the GFCI. The grounding conductor provides the necessary grounding path for the GFCI to function properly. It's also worth noting that some jurisdictions may have local amendments to the NEC that impose stricter grounding requirements. Therefore, it's essential to consult with local building codes and regulations to ensure compliance. In conclusion, while the NEC does provide an exception for non-self-grounding GFCIs in certain situations, it's crucial to understand the underlying principles of grounding and bonding. Proper grounding is essential for electrical safety, and it's important to ensure that all electrical devices, including GFCIs, are properly grounded according to the requirements of the NEC and local codes. Always consult with a qualified electrician if you have any questions or concerns about grounding requirements. Now, let's further expand on the topic of GFCI grounding by discussing the specific requirements for conductor sizing and installation practices. The size of the grounding conductor used for GFCI installation is determined by the size of the circuit's ungrounded conductors, as specified in NEC Table 250.122. The grounding conductor must be sized appropriately to safely carry the fault current back to the source, allowing the circuit breaker or fuse to trip and to energize the circuit. In addition to proper sizing, the grounding conductor must also be installed correctly. It should be run in the same raceway or cable as the circuit conductors, and it should be securely connected to the grounding terminals of the GFCI and the electrical box. When connecting the grounding conductor to a metal box, it's important to ensure that the connection is made with a listed grounding connector. These connectors are designed to provide a reliable and low impedance connection between the grounding conductor and the metal box. It's also crucial to avoid damaging the grounding conductor during installation. Nicks, cuts, or abrasions can reduce the conductor's ability to carry fault current and compromise the safety of the installation. When working with metal conduit, it's important to ensure that the conduit is properly grounded. This can be achieved by using listed grounding bushings and bonding jumpers to connect the conduit to the building's grounding electrode system. Grounding bushings are installed at the ends of the conduit and provide a smooth, rounded surface for the grounding conductor to pass through. Bonding jumpers are used to connect sections of conduit together and to connect the conduit to other metal enclosures. In addition to the requirements for grounding conductors and metal conduit, the NEC also specifies requirements for grounding electrodes. A grounding electrode is a conducting object that is used to connect the building's electrical system to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the minimum size and installation requirements for grounding electrodes, and it also requires that grounding electrodes be tested to ensure that they have a low impedance connection to the earth. The impedance of the grounding electrode is a measure of its resistance to the flow of current. A low impedance grounding electrode provides a more effective path for fault current to flow back to the source, reducing the risk of electrical shock. In some cases, it may be necessary to install multiple grounding electrodes to achieve a low enough impedance. The NEC also addresses the use of surge protective devices, or SPDs, in electrical systems. SPD are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or power line disturbances. SPD are typically installed at the service entrance of the building, and they are connected to the building's grounding electrode system. When a voltage surge occurs, the SPD diverts the surge current to ground, protecting the electrical equipment from damage. It's important to ensure that SPD are properly grounded to function effectively. The grounding conductor for an SPD should be as short and straight as possible, and it should be connected to a low impedance grounding electrode. In addition to the technical aspects of GFCI grounding, it's also important to consider the practical implications of these requirements. When installing a GFCI, it's always a good practice to visually inspect the grounding connections to ensure that they are secure and properly made. A loose or corroded grounding connection can compromise the safety of the installation and increase the risk of electrical shock. It's also important to test the GFCI after installation to ensure that it is functioning properly. This can be done by pressing the test button on the GFCI and verifying that the device trips and cuts off power to the circuit. If the GFCI does not trip, it may be defective and should be replaced. Finally, it's important to remember that electrical work can be dangerous, and it should only be performed by qualified individuals. If you are not comfortable working with electricity, it's always best to consult with a licensed electrician. They can ensure that the electrical system is installed safely and in accordance with the requirements of the NEC and local codes. Now, let's discuss some common misconceptions about GFCI grounding. One common misconception is that a GFCI will always protect against electrical shock, regardless of the grounding conditions. While GFCIs provide excellent protection against ground faults, they do not protect against all types of electrical shock. For example, a GFCI will not protect against shock from contact with two energized conductors, such as the hot and neutral wires in a circuit. Another misconception is that a self-grounding GFCI does not require a grounding conductor. As discussed earlier, even self-grounding GFCIs must be connected to a properly grounded circuit. The self-grounding feature only provides a convenient way to connect the GFCI to the metal box, but it does not eliminate the need for a grounding conductor. A third misconception is that a GFCI can be used to replace a missing grounding conductor. GFCIs are not a substitute for proper grounding. If a circuit does not have a grounding conductor, it should be rewired to include one. GFCIs can provide additional protection on circuits that already have a grounding conductor, but they cannot replace the grounding conductor entirely. It's also important to note that GFCIs have a limited lifespan. Over time, the electronic components in a GFCI can degrade, reducing its ability to protect against ground faults. Therefore, it's recommended that GFCIs be tested periodically and replaced as needed. The frequency of testing will depend on the environment in which the GFCI is installed. GFCIs installed in damp or corrosive environments may need to be tested more frequently. In addition to the NEC requirements for GFCI grounding, there may also be local codes or regulations that apply. It's important to check with the local building department to determine if there are any additional requirements in your area. Local codes may be more stringent than the NEC in some cases, and it's important to comply with all applicable regulations. Finally, it's important to stay up to date on the latest changes to the NEC. The NEC is updated every 3 years, and the changes can affect the requirements for GFCI grounding. It's a good idea to subscribe to a reputable electrical newsletter or attend electrical training courses to stay informed about the latest changes to the NEC. Understanding the NEC requirements for GFCI grounding is essential for electrical safety. By following these requirements and using proper installation practices, you can help to protect yourself and others from electrical shock hazards. Always consult with a qualified electrician if you have any questions or concerns about GFCI grounding or any other electrical issue. They can provide expert advice and ensure that your electrical system is installed safely and in accordance with all applicable codes and regulations.